This video is a continuation of the walkthrough on answering the worksheet, naming organic compounds. This worksheet again is made by Vancouver Community College, and yeah, we'll be using it for the lesson. Okay, so let's go start with number 9. For number 9, we have D-nitrotoluene. I'm not exactly sure how to. Yeah, to start with, the teacher never taught this. We'll do that later. Or yeah, let's do it now. We'll be searching another word for that. Surely there is. 2 for dinitrotoluene. 2 for dinitrotoluene. Another word. Wi-Fi is really slow. Alright. Yeah, I'm not sure about number 9. Let's go with number 10. 3-ethyl, 2-dimethyl, 2-pentanol. So pent, that means we have 5 carbons in the parent chain. There are 2 methyls on the second and third carbon respectively, and there is 1 ethyl substituent on the third carbon. So first we illustrate the number of carbons. So we have 5 of them, and then 3-ethyl. This is where we have the ethyl substituent. So we have this one. Is my voice okay? Good. And then 2,3-dimethyl. So there's a methyl here in the third carbon also, and another methyl in the second. I'm not sure if this policy applies, but in this scenario, we are trying to we count from left to right. So 1, 2, 3, 4, 5. I'm not sure if there's a policy called exactly to this, but then I think there is. I'm not sure though if it's exactly that kind of policy. There's S and R naming compound thing. There, rectus and sinister. Although this isn't taught in our class yet, I came across this a few minutes ago, and yeah, it's weird, but I think we are following the rectus. I think rectus is an equivalent of clockwise, or in other words, reading from left to right. If it's reading invertedly or from right to left, or counterclockwise, then that's called sinister, or the S, in the context of naming organic compounds. So sinister and rectus. But I'm not sure though. That's just my hypothesis. Now don't blame me if I'm wrong, because again, the teacher never taught that topic yet. So anyways, this is the structure for number 10. 3-ethyl, 3-dimethyl, 2-pentanol. Oh yeah, by the way, 2-pentanol, we have OL, so this is basically alcohol, and alcohol is located at the second carbon, so we remove hydrogen there and we replace it with alcohol, which is OH. Again, alcohol has a template R, C, and then no, R and then just OH. So yeah, that's for alcohol. That's for number 10. Let's move on to 11. 5-chloro-4-methyl 3-hepta. Hepta means 7 carbons. So 1, 2, 3, 4, 5, 6, 7. I apologize if you hear any background noise here. This public place isn't exactly a place where we could silently work, do our thing on laptops and iPads. But yeah, the place where I am usually birthdays and stuff. Kind of annoying, but yeah, it's alright. As long as we're doing the topic, then that's fine. 5-chloro. So this is we have chlorine in the 5th carbon. So that's a substituent associated with alkyl halide. We all know that chlorine is one of those halogens. So as long as there is a halogen together with anything else that is also functional group, then that's definitely an alkyl halide. So how do we know where to count? From left to right or from right to left? In this scenario, it doesn't really matter. But then I personally prefer, which is still correct, universally correct. I prefer to read from left to right. So known, that is the suffix for ketone. Again, ketone is a part of the carbonyl group, which looks like this. It's similar to what ester looks like as a template, but yeah, I hope you notice the difference. Ester is oxy, ketone is known in terms of prefix, suffix, that kind of thing. So 5-chlorine, we count from left to right, 1, 2, 3, 4, 5. So chlorine is here. Any position would do. If you put chlorine below and hydrogen at the top, then it doesn't really matter. It's still the same. 4-methyl. We have methyl here. And then 3-heptanol. Ketone is located in the 3rd carbon. So I bet it's like that. We don't put any connection below because, as you all know, carbon can only be associated with 4 connections. So this is connection 1, connection 2, connection 3, connection 4. Ketone, this is naturally a part of ketone. As a member of the carbonyl group, there will always be this kind of figure. Oxygen at the top that is connected with two bonds. That makes a double bond connected to carbon, and any other. R basically stands for any other connection that's connected to it. So add all the H's, the hydrogens. So we're done with 4-methyl, we're done with 5-chloro, we're done with placing ketone in the 3rd carbon. Let's just put the rest of the hydrogens. Then we're done. By the way, I almost forgot. Let's compare number 10 with the answer key as well as 11. Let's assess if we got them precisely or accurately at most. Okay, for number 10, let's see. Okay, CH3. We have methyl at the top. We have OH below. We have CH3 at the top. CH2, CH3 below. This is the ethyl, and this is the methyl. And CH2, this is CH2, CH3, this is CH3. So as you can see, we got them all present. All of the parts that are written in the answer key, they're all present in my drawing, in my illustration. Let's go with number 4. Number 4, first carbon there, 2nd carbon, 3rd carbon. As you can see, it exactly looks the same. And then CH, CH, and then CH3, CH3. CH is this one, and then chlorine, top below doesn't really matter. I suspect there is something wrong with the answer key. The carbon is only connected to 3. There is supposed to be something else, don't you think? or maybe I'm just hallucinating. Who knows? It's up for you to decide. Maybe which is wrong, my illustration or the illustration of the answer. There must be a typo, maybe, but I'm pretty positive there actually is. CH2 and then CH3. So everything's present and accounted for. So far so good. This region will just be a topic of debate because we all know that carbon is supposed to be associated with 4, no more no less, 4 things. And there's supposed to be H there, which makes these H2. But I'm not sure why they didn't put it like that. Well, maybe not this. Not this either. I wonder why. I don't know anymore. Let's go with 12. So phenyl is, in other words, benzene, I think, as part of the phenyl group. And then we have prop, so that means we have 3 carbons in the parent chain. The triple bond is located in the first carbon, so 3 phenyl. Phenyl must look like this, and then benzene looking. Let's see if I got it right. What's number 12? Okay. H and then C and then triple bond C. The same as this. Yeah, my only mistake is that I'm supposed to bring this entire chunk. There's supposed to be CH2 here, and then it's connected like this way. Okay, I think that's it. Let's go with part C. We have no space anymore. Add one more page. We are commissioned in letter C to draw open chain structures following molecular formulas and naming them. Well, I can't assure you that I'd be able to draw all the possible stuff, but yeah, we'll give it a try. Wait, open chain structures. For, let's say, structure formula of number 1. This is 5 carbons, so pent, and then 12. 1, 2, how many? Let's count the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is all single bond alkane. So this is pentane. Pent for having 5 carbons in the parent chain, and ane because it's only single bond. So this is called pentane. For number 2, we still have the same number of carbons in the parent chain, still pent, but then this time we have 10 carbons. So what do we do if that's the case? So let's see. We have there has to be a double bond in order to reduce the amount of hydrogens. So let's say we put the double bond here in carbon 2. Any position would do, but yeah, I prefer to place them here right now. So if you count the carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are hydrogens, not carbons. If you count the hydrogens, there are 10 in total because there is a double bond. Why is there a double bond? Why does it contribute to reducing the number of hydrogens? Well, 1, 2, 3, 4. That is the maximum number of connections a carbon can have because a carbon has the maximum of 4 valence electrons. And as well as this one. Still the same. 1, 2, 3, 4. Can only connect to 4 maximum. For number 3, we have C3H8 and then O. I wonder how this is gonna turn out to be. We have 3 carbons, so this is prop. So let's try to add the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. This is weird. Why is oxygen here? Where is it supposed to be stationed? Everything's already connected to each other. I wonder. Answer key, please. I give up. Oh wait, this is C. Okay, I get it. Any side would do, but just place OH. So that's gonna be 1 propanol. Assuming that we count from here to the left, from right to left. So this is the first carbon, second, and third. So in that case, that's 1 prop. No. Well, I can't really say all the possible figures, but then for number 2, it's 2 propanol. Basically, what happens there is that you just moved your OH in the middle, in the second carbon. Regardless if you read from left to right, right to left, it's still the same thing. It's still 2 propanol. For the third one, the third possibility, mesoxyethane, something associated with ether. I don't advise you to write it this way. I advise you to write the UPAC version of an organic compound, because I'm telling you right now, your teacher might not appreciate it. It might be a deduction. So, mesoxyethane. So the prefix is mes and then suffix is ethane. So that means we have CH3 at the left side and then separated with O. We all know that ether, the template is ROR. So I hope you can visualize it in the context of this example. This is the O, and then this is the R, and the other R is this region. So this one represents meth, and then this one is oxy, and then this one is ethane. Therefore, it looks like the given exactly looks like what I just drew. So yeah, that's it. Let's talk more about the numbers 1 and 2. By the way, I almost forgot. For number 2, this is 2-pentene. Why did I place 2? Because the double bond is located at the second carbon. Okay, one more page. After discussing this, we're done. We're officially done with the worksheet. So, methylbutane. So basically, we have 4 carbons, 2 methyl, so methyl will be here. And then butane, this is all single bond, so yeah. That's it for 2-methylbutane. The only difference is the substituent in the second carbon. How about 2,2-dimethylpropane? So let's borrow this part so we can write faster. So basically in propane we have in propane single bond with 3 carbon atoms. So in the middle, in the second carbon, this one, we have 2 methyls. So CH3 below, CH3 above. I just said it was the other way around. Anyways, H. That's it. Let's try 2-pentene, this one. So pent is 5 carbons, so 1, 2, 3, 4, 5. And then 2, let's say this is the second carbon. So we put there the double bond. You know what? Yeah, never mind. I just place the hydrogens that way, and then there we go. So that's it for 2-pentene. So far so good. Wait, no, I'm supposed to write another hydrogens there so that it makes 4. 1, 2, 3, 4. Okay, that's for 2-pentene. Finally, 2-methyl 1-butene. Pretend that you haven't seen the answer yet, but let's draw it. But, so 1, 2, 3, 4, and then in the first carbon there is the double bond because of the E and E. So there, assuming that this is how we count, we can start from left to right, not right to left. Any way we do, any is correct in this scenario. 2-methyl, so the second the methyl substituent is located in the second carbon, so this is CH3, and then everything else write the hydrogen. So as you can see, hang on, this is supposed to be not there because again carbon can only link to 4. There you go. So this is CH2, the double bond, and with the C, the CH3, the CH2, the CH3. There you go. Okay, that's it. I apologize for that mistake. At least you know that that extra H isn't supposed to be there. As always, carbon is supposed to be linked with 4, no more, no less. Otherwise, better check your answer. That's it for this video. Thank you for watching, and I hope it helps.